In this video, we will be learning some of the basic rules of chemical nomenclature. Whenever you start a topic in science, the whole thing feels like a big mystery. And the first step in demystifying it is to understand the meaning of every word you come across. This involves looking at science as a language, with its own set of vocabulary terms and grammar rules. No, you will not find this language on Babbel or Duolingo, and it's something that you will simply need to teach yourself. But once you take on that challenge, and once you make a pact with yourself that you will not move ahead until you understand every term you encounter, your progress will become that much faster and your comprehension that much deeper. So, who developed this language of science, and who is in charge of all the rules? Since 1919, an organization called IUPAC, the International Union of Pure and Applied Chemistry, has been the recognized authority on all things chemistry. Its goal is to establish uniform and consistent rules so that worldwide scientists can use the same conventions and communicate without confusion. And to this end, the rules of chemical nomenclature are set in stone. The topic is huge, but we will narrow it down to chemical nomenclature of binary compounds. Let's define each word in the title. Chemical refers to the study of chemistry or the study of how substances react. Nomenclature is any system devised for naming things. Binary means made up of two parts, and compounds are substances made up of more than one element. So this topic involves the study of the rules for naming chemical substances that are composed of two different elements. By the end of this video, you will be able to apply these rules of nomenclature to a specific category of formulas. For example, you will be given a formula such as SiF4, and you will be able to identify it by its correct name, silicon tetrafluoride. But to get there, you must be able to determine whether an element is a metal or a nonmetal. For that, you will examine the periodic table to learn about its organization and how it separates these two classes of elements. And as a bonus, you will uncover some revealing consistencies about the names of the elements of these two groups so that you will know from its name whether an element is a metal or a nonmetal. This is how we will proceed. Critical to understanding nomenclature rules is the ability to identify an element as a metal or a nonmetal. Let's do a quick review of how to do that. As of 2020, there are officially 118 elements on the periodic table. Due to their physical and chemical properties, most of these are classified as metals. An arbitrary zigzag line separates them from the nonmetals. Just along the boundary between the metals and the nonmetals, located on either side of the zigzag line, 7 elements show characteristics of both metals and nonmetals. They are classified as metalloids, which means metal-like. In a compound, they may behave either as a metal or a nonmetal. At this level of nomenclature, You won't come across too many compounds that contain metalloids. From what we have seen so far, we can certainly begin to appreciate that the location of an element on the periodic table gives so much information about its characteristics. You might think of it as how some addresses can give an idea of the real estate in an area. We have seen that the left-hand side of the periodic table houses the metals. Isn't it fascinating that the majority of the elements on the table, that is, the majority of the discovered elements in our universe, are metals? And by comparison, only a small number of elements are nonmetals. These, with the exception of hydrogen, are all located on the far right-hand side of the periodic table. Hydrogen's placement with the metals is an anomaly. On many periodic tables, it is shown disconnected from the main table, floating just over the first group called the alkali metals. I like that presentation because it points to the fact that though it is not an alkali metal, hydrogen behaves as one in terms of its high reactivity. All you need to remember is that being a gas in its natural state, hydrogen cannot possibly be a metal. So in your mind, have it scoot over to the other side. We've covered quite a bit. How about a short quiz to check your understanding? I will ask 8 questions, giving you a chance to answer them. At these visual prompts, pause the video, think about the answer, then click to resume the video and to check your answer. Question 1. Where are the metals located on the periodic table? The metals are located on the left-hand side of the zigzag line on the periodic table. Question 2. Where are the nonmetals located on the periodic table? Answer. The nonmetals are located on the right-hand side of the zigzag line on the periodic table. An exception is hydrogen, which is located on the far left-hand side on the top. Question 3. Where are the metalloids located on the periodic table? The metalloids are located just along the border of the top part of the zigzag line, touching it on the left and right. Question 4. An element located here on the periodic table will be A, a metal, B, a nonmetal, or C, a metalloid. This element will be a metalloid. Question 5. An element located here on the periodic table will be A, a metal, B, a nonmetal, or C, a metalloid. This element will be a metal. Question 6. An element located here on the periodic table will be A, a metal, B, a nonmetal, or C, a metalloid. This element will be a metal. Question 7. An element located here on the periodic table will be A, a metal, B, a nonmetal, or C, a metalloid? This element will be a nonmetal. And the last question, question 8. An element located here on the periodic table will be A, a metal, B, a nonmetal, or C, a metalloid. This element will be a nonmetal. Well done! Here is your certificate of understanding. You did very well on that quiz. But you seem puzzled, Alejandro. Do you have any questions?
Yeah. So before I can name a binary compound, I have to know what it's made of?
Yes, that's correct. You need to know whether each component is a metal or a nonmetal.
Then will I need to look up every element on the periodic table?
The good news is that you don't. At some point, you will become familiar with many of the elements commonly found in binary compounds. Let's check out the metals. Most of you already know that iron, nickel, copper, silver, tin, and gold are metals. Other metals, such as manganese, cobalt, zinc, tungsten, mercury, lead, and bismuth, may be more obscure. But what is extremely helpful is to know that most elements whose names end in are metals. One notable exception is helium. We are all well acquainted with helium balloons and helium gas. So like hydrogen gas, helium gas cannot possibly be a metal, despite the ending. Besides helium, there's only one other nonmetal whose name ends in and that is selenium. So, besides the ones that are familiar and the ones that may be more obscure, if the name ends in the element is a metal, except for helium and selenium. The names of 3 metalloids, germanium, tellurium, and polonium, also end in If you do come across them, you would be safe to treat them as metals. The most common nonmetals you will come across are the group 7 halogens. Listen to their names: fluorine, chlorine, bromine, iodine, astatine, and tennessine. Notice the "ene" ending? Think of it this way. If it ends in "ene", it's a halogen, which is a nonmetal. And the remaining more common nonmetals, carbon, nitrogen, oxygen, phosphorus, and sulfur, are also easy to remember if you think of them as C-nops. And though we've covered them already, I will stress one more interesting consistency. The names of 3 elements, hydrogen, nitrogen, and oxygen, end in gen. You will find them in many binary compounds. Just remember that they are gases and therefore nonmetals. Other elements you will not need to look up are those of the last group, Group 8, which are called the noble gases. Because for the most part, the noble gases do not react with other elements, it is unlikely that you will encounter them when you're looking at binary compounds. Still, I would be remiss if I didn't point out a telling consistency in their names that would help you classify them. We've already talked about helium, but there's also neon, argon, krypton, xenon, radon, and oganesson. For sure you notice the common on ending on all but helium.
Wouldn't it be neat if helium was called helon? I have a question. I have a question. Question. A question here.
Yes, Joey, what is your question?
So all elements that end in on are noble gases?
Well, that's not quite right. Let's look at the periodic table. 3 elements, boron, carbon, and silicon, also end in on, and they are not noble gases. In fact, carbon is the opposite of the noble gases in terms of its ability to combine with other elements. Because it can bond in many different ways, carbon can form innumerable compounds. So to summarize, with the exception of helium, the names of all the noble gases end in on. And keep in mind that not every name that ends in on is a noble gas. Boron, carbon, and silicon also end in on, but they are not noble gases. A Venn diagram would make this information much easier to understand. Using it, we can present the individual characteristics of each set and highlight the characteristics common to both sets. Here's how it would look for the information we just learned. The yellow set includes the names of all the elements ending in on. The blue represents all the noble gases. The area where they merge, the green, represents all the noble gases whose names end in on. So, before you run to the periodic table each time you want to name a compound, check your own knowledge. Get into your head. What's the name? It's a metal if it ends in except for helium and selenium. It's a nonmetal if it's one of the CNOPS group or if it ends in -ene or -gen or -on. And if you can't remember, no problem. You simply pull out your periodic table. Let's take another look at our learning objectives to see where we stand. Just remind yourself that in order to learn the rules of binary nomenclature, you need to be able to tell whether an element is a metal or a nonmetal. You have learned how to do this in 2 ways. 1, from the name of the element, and 2, from the periodic table. It is now a good time to check your understanding with a short quiz. After that, we will proceed to the main lesson, which is to learn the rules of binary nomenclature and to apply them. You will be given 8 questions on this quiz, each one asking you to classify a certain element as a metal or a nonmetal. First, you will classify it based on its name, then you will confirm your answer from its location on the periodic table. To engage in your learning, just follow the prompts. Question 1. Is chlorine a metal or a nonmetal? Based on its name, chlorine, which ends in -ene, is a halogen and therefore a nonmetal. Its location on the right-hand side of the zigzag line on the periodic table indicates that it is a nonmetal. Question 2. Is magnesium a metal or a nonmetal? Based on its name, magnesium, which ends in is a metal, and its location on the left-hand side of the zigzag line on the periodic table indicates that it is a metal. Question 3. Is iron a metal or a non-metal? Iron, a very common element, is a well-known metal, and its location on the left-hand side of the zigzag line on the periodic table indicates that it is a metal. Question 4. Is selenium a metal or a non-metal? Because it ends in you might think that selenium is a metal. Just remember that like helium, it is an exception to the rule. Selenium is a non-metal. Its location on the right-hand side of the zigzag line on the periodic table indicates that it is a non-metal. Question 5. Is hydrogen a metal or a non-metal? Based on its name, hydrogen, which ends in gen, is a gas, and therefore a non-metal. Its location on the left-hand side of the zigzag line on the periodic table might indicate that it is a metal, so you just need to remind yourself that it belongs to the other side. Question 6. Is phosphorus a metal or a non-metal? Phosphorus belongs to the CNOPS group. It is a non-metal. Its location on the right-hand side of the zigzag line on the periodic table indicates that it is a non-metal. Question 7. Is mercury a metal or a non-metal? Because of its harmful effects on the nervous system, mercury has become less commonplace than it used to be. It is a metal with the interesting characteristic that it is a liquid at room temperature. Its location on the left-hand side of the zigzag line on the periodic table indicates that it is a metal. The last question, question 8. Is krypton a metal or a non-metal? With the exception of boron, carbon, and silicon, all names that end in on are noble gases and therefore non-metals. Krypton's location on the right-hand side of the zigzag line on the periodic table indicates that it is a non-metal. It's time to get back to our main goal. You now know how to classify an element as a metal or a non-metal, and by doing so, you have set for yourself the foundation for learning the rules of nomenclature. A fun way to do this is to work backwards and to uncover them through discovery learning. By carefully considering the names, looking for patterns, and analyzing the patterns, you will figure out the grammar rules behind the names. It will be like cracking the code behind the enigma. Start by familiarizing yourself with the chemical names that you will be encountering. I will call out the name, and then you can repeat it after me. Are you ready? Let's go! Chlorine tetrafluoride. Lithium sulfide. Trinitrogen pentaphosphide. Carbon dioxide. Aluminum carbide. Sulfur trioxide. Potassium iodide. Sodium fluoride. Magnesium chloride. Disilicon hexabromide. We'll now start to decipher the rules. I will be asking questions, giving you a chance to answer them. When you see the prompts, pause the video, think about the answer, Then click to resume the video and to check your answer. Here is the list of our 10 compounds. Let's look for patterns, for similarities and differences in their names. What two characteristics do all the names have in common? That's right. All the names are made up of two parts, like a first and last name, and they all end in "ide." How are they different? You got it. Some names have prefixes like the di and tri and tetra that we have in math, and others don't. We notice that there are two styles of nomenclature in this set of 10 compounds. We'll separate the two groups according to style. And label them as Group 1 and Group 2 for easy reference. Then we will try to figure out the reason for the two styles. Could it be that the styles differ according to the elements that comprise the compounds? Let's check that out by writing down the elements that comprise each compound. Are you ready to do that? I'll start you off with carbon dioxide. Carbon dioxide is made up of carbon and oxygen. Now you do the same for the remaining 9 compounds. How did you do? Next, you will examine each pair of elements that make up the compounds. How would you classify each element? Is it a metal or a non-metal? And because that's going to be a lot of information to handle, we should set up a chart to organize our records. We'll put in the information we already have. And then work on the element classification column. If you can remember without looking them up, that's great. And if not, you can always pull out a periodic table. I'll help out with the first pair. That's carbon and oxygen. Then you complete the rest. Carbon is one of the CNOPS group. It's a nonmetal. Oxygen ends in gen. It's a gas and therefore a nonmetal. Now you do the rest. It's time to note the patterns. Express your findings by filling in the 4 blanks in these statements. In Group 1, the first element is always a nonmetal. The second element is always a nonmetal. In Group 2, the first element is always a metal. The second element is always a nonmetal. So we have a non-metal combination and a metal-nonmetal combination. Notice that in both cases, the second element is a nonmetal. Due to how elements bond together, metal-metal combinations are not possible, and therefore, in binary compounds, the second element will never be a metal. You've made a lot of observations. Another table will help you organize what you have learned. Can you fill in the chart? Now check your answers. How did you do? An excellent learning skill is to review your material from different perspectives. One might think of it as overlearning, but in my books, that's always a good thing. Let's see how we can apply that practice. In the last chart, you tabulated the characteristics of the two groups of binary compounds and began to make note of the similarities and differences in the two styles. Now, we'll consolidate our observations from a different perspective and use, once again, a Venn diagram to highlight these similarities and differences. By looking at our information in different ways and from different angles, we can really begin to understand it. But we're not quite done. A closer scrutiny of the names will complete our study. So far, we've looked at the full name of the binary compound to try to figure out the rules. Now, in a second phase of the study, let's examine what happens to the names of the first and second elements individually. We'll begin our observations on the first element, go through both groups, and then repeat the process for the second element. In preparation, I'll ask Eric to pull up the periodic table. Thank you, Eric. Then, to help us focus on the relevant parts, we will cut up the table. We'll start with group 1. Because all the first elements in this group are nonmetals, the nonmetal side of the periodic table is all that we need. Let's disregard the prefixes and compare the names with those on the periodic table one by one. Carbon matches carbon. Sulfur matches sulfur. Chlorine matches chlorine. Nitrogen matches nitrogen. And silicon matches silicon. We note that if we disregard the prefixes, the names of the first elements match those on the periodic table. Now on to group 2. In group 2, the first element is a metal and there are no prefixes to contend with. Let's pull out the relevant side of the periodic table and go through the names one by one, matching them with those on the periodic table. Lithium matches lithium. Magnesium matches magnesium. Potassium matches potassium. Sodium matches sodium. And aluminum matches aluminum. Once again, we note that the names of the first elements match those on the periodic table. We can now record our findings. If we disregard the Greek prefixes that we encounter in nonmetal compounds, we can make a general statement about the first element. In a binary compound, the name of the first element remains unchanged. We'll now check out the second element for both groups, once again disregarding the number prefixes that we find in group 1. We've already noted that the name of a binary compound ends in "ide." We also noted that the second element is always a nonmetal. This means that names that end in "ide" are nonmetals. Recall that on the periodic table, none of the names ends in "ide." So how do we figure out the "ide" ending?
Is there a rule for how to get the "ide" ending?
No, Joey, unfortunately not. In general, to get the "ide" ending, a few of the last letters of the element's name are dropped and the suffix "ide" is added on. But how many letters are dropped is different for different elements. You simply have to memorize the correct "ide" name for each nonmetal element. Remember, science is a language, and this is the vocabulary part. So let's get started with learning them. As always, a chart helps. We'll set one up and begin with the first sample on our list. Oxide refers to the element oxygen. The letters YGEN are dropped off its name and replaced by "ide." Oxygen becomes oxide. It is a common second element in binary compounds. Here it is once again. Next on our list is fluoride, which refers to fluorine. The halogens are easy. Their "ine" ending is dropped and replaced by "ide." Fluorine becomes fluoride. Phosphide refers to phosphorus. Bromide refers to bromine. Sulfide refers to sulfur. Chloride refers to chlorine. Iodide refers to iodine. We've already discussed fluoride, and carbide refers to carbon. Others you will encounter are hydride for hydrogen, boride for boron, nitride for nitrogen, and silicide for silicon. We'll record our findings and make a general statement about the second element. In a binary compound, the ending of the name of the second element is deleted and replaced by "ide." And finally, a look at the prefixes.
Δεν καταλαβαίνω τίποτα.
Yes, it's Greek to everyone. But you've seen these before. If, like in math, these prefixes mean numbers, is it possible that in chemical names they refer to the number of atoms of each element? A simple way to check out this hypothesis is to look at the formulas of the compounds to see how they relate to their names. We'll do this only for group 1 because that's where we encounter prefixes. Carbon dioxide is CO2. Sulfur trioxide is SO3. Chlorine tetrafluoride is ClF4. Trinitrogen pentaphosphide is N3P5. And disilicon hexabromide is Si2Br6. Now match the prefixes in the names with the numbers in the formulas. Just like math, isn't it? So yes, these prefixes come from the Greek language and they mean the exact same thing in both math and science. Make sure you know them. And we're left with one rule that we haven't covered yet. You might get a hint of that rule if we review the compounds in our last chart. Going in reverse order, the name disilicon hexabromide indicates that there are 2 atoms of silicon and 6 atoms of bromine. Clearly, the name spells out the formula, and the formula spells out the name, except that in the name, the number comes before the element, and in the formula, the number comes after the element. Trinitrogen pentaphosphide follows the same pattern. There are 3 atoms of nitrogen and 5 atoms of phosphorus. Once again, the name spells out the formula, and the formula spells out the name. Now, with chlorine tetrafluoride, things get interesting. If, as you may already know, the absence of a subscript in a formula indicates the number 1, then the formula ClF4 describes a compound with 1 atom of chlorine and 4 atoms of fluorine. But if we followed the rules, shouldn't the name be monochlorine tetrafluoride? Shouldn't SO3 be monosulfur trioxide? And shouldn't CO2 be called monocarbon dioxide? To make sense of these names, we'll examine another list of non-metal compounds. In our new list, we have carbon monoxide, CO, carbon dioxide, CO2, nitrogen monoxide, NO, nitrogen dioxide, NO2, and dinitrogen dioxide, N2O2. The hidden rule should now come to light. We see that the prefix mono only appears with second elements, and there is our rule. The prefix mono is only used on the second element, not on the first. Did you notice how we went about learning the rules of binary nomenclature? We made the discovery process parallel a science experiment. We set a goal, used the appropriate materials, developed a structured procedure, made observations, and recorded them in various charts. And now it is time to draw our conclusion. We can conclude that there are 2 groups of binary compounds. In the first group, we have a non-metal element followed by a non-metal element, and in the second group, we have a metal element followed by a non-metal element. These 2 groups have 3 characteristics in common. They both have 2 parts to their name, they both have a first name which matches that on the periodic table, and they both have a second name that ends in "ide." The main difference is that the non-metal group uses Greek prefixes, and the metal-non-metal group does not. Here is a way to remember the most important information of this conclusion. Non-metal Greek, metal-non-metal non-Greek. Note the 2 nons in each part. If you can remember this jingle and know how to apply it, you have mastered chemical nomenclature of binary compounds. All right, it's time to check your knowledge. I'll give you several formulas for binary compounds, and you give me their names. We'll do the first 2 together. Question 1 will be an example of a non-metal compound, and question 2 will be an example of a metal-non-metal compound. Are you ready? Question 1. What is the name for N3P5? Let's work through the answer for this. N3P5 is composed of 2 different elements. Therefore, it represents a binary compound. The symbol capital N stands for nitrogen, and the symbol capital P stands for phosphorus. Either from their names or from their location on the periodic table, you determine that they are nonmetals. So, as a nonmetal compound, the name will include Greek prefixes and it will be spelled out by the formula. With this information in mind, we can start constructing the name. As the first element, the name nitrogen will stay the same, but there are 3 atoms of nitrogen, so we add the prefix tri. The first name in the compound is trinitrogen. As the second element, the name phosphorus drops its ending, changing it to "ide." The name becomes phosphide. There are 5 atoms of phosphorus, so we add the prefix penta. The second name in the compound is pentaphosphide. Thus, the name for the formula N3P5 is trinitrogen pentaphosphide. And as with all nonmetal binary compounds that contain Greek prefixes, the name spells out the formula, and the formula spells out the name. Question 2. What is the name for Al2O3? Let's work through the answer for this. Al2O3 is composed of 2 different elements. Therefore, it represents a binary compound. The symbol capital A small l stands for aluminum, and the symbol capital O stands for oxygen. Either from their names or from their location on the periodic table, you determine that aluminum is a metal and oxygen is a nonmetal. So, as a metal-nonmetal compound, the name will not include Greek prefixes. With this information in mind, we can start constructing the name. As the first element, the name aluminum will stay the same. We note that there are 2 atoms of aluminum, but because this is a metal-nonmetal compound, there will be no Greek prefixes. The name leaves out the numbers, and the first name in the compound is aluminum. As the second element, oxygen drops its ending, changing it to "ide." The name becomes oxide. There are 3 atoms of oxygen, but once again, the number is left out in the name. The second name in the compound is oxide. Thus, the name for the formula Al2O3 is aluminum oxide. And as with all metal-nonmetal binary compounds, there are no Greek prefixes. Of course, you may wonder how, if there are no prefixes in the name, can one figure out the formula? Well, there's a way of doing that, but that is a subject for another lesson, another video. Question 3. What is the name for Se2O? Answer: diselenium monoxide. Remember that though selenium ends in it's a nonmetal. Question 4. What is the name for NO2? Answer: nitrogen dioxide. Question 5. What is the name for K3N? Answer: potassium nitride. Question 6. What is the name for Si2Br6? Answer: disilicon hexabromide. Question 7. What is the name for Mg3N2? Answer: Magnesium nitride. Question 8. What is the name for LiF? Answer: lithium fluoride. Question 9. What is the name for Pi3? Answer: phosphorus triiodide. Question 10. What is the name for Na2O? Answer: sodium oxide. Question 11. What is the name for SCl4? Answer: sulfur tetrachloride. Question 12. What is the name for Li2S? Answer: lithium sulfide. Question 13. What is the name for IBr? Answer: iodine monobromide. Question 14. What is the name for Si3N4? Answer: trisilicon tetranitride. Question 15. What is the name for P4S7? Answer: tetraphosphorus heptasulfide. Question 16. What is the name for Ki? Answer: potassium iodide. Question 17. What is the name for Al4C3? Answer: aluminum carbide. Question 18. What is the name for SeF6? Answer: selenium hexafluoride. Question 19. What is the name for MgCl2? Answer: magnesium chloride. Question 20. What is the name for BeF2? Answer: beryllium fluoride. Question 21. What is the name for Al2S3? Answer: aluminum sulfide. Question 22. What is the name for Sr3P2? Answer: strontium phosphide. Question 23. What is the name for Li2O? Answer: lithium oxide. Question 24. What is the name for NaCl? Answer: sodium chloride. Question 25. What is the name for NF3? Answer: nitrogen trifluoride. Question 26. What is the name for XeF4? Answer: xenon tetrafluoride. Yes, this one's a surprise. You've learned that the noble gases are unreactive, so you would not expect to see xenon, a noble gas, in a compound. But you can think of it this way. Fluorine is so reactive that it even reacts with the most reluctant element. Question 27. What is the name for CaS? Answer: calcium sulfide. Question 28. What is the name for Rb3p? Answer: rubidium phosphide. Question 29. What is the name for SiH? Answer: silicon monohydride. Question 30. What is the name for BeH2? Answer: beryllium hydride.
Good job! I'm done!
Congratulations! You are now able to name a binary compound when you're given its formula. In the next lesson, you will learn how to derive the formula when you are given the compound's name. Thank you for watching. I hope this video was helpful.